This webcast continues Worksheet 8D and looks at problems 6 and 7. Okay, so in problem 6 we have a bungee jumper. And initially this person is at the top of a really tall platform. And so they're very high. Let's see if I can get over there. So they're high and they're not moving. Right, they're just standing up there waiting to step off. And at position B, notice they're not quite on the ground. So they're at a lower position, but they're not on the ground. So they've still got a little bit of height, but they're not moving. Okay. And it says too that this system is frictionless, so we're not going to have any dissipation. And the system includes the person, the jumper, the bungee cord, and the earth. Okay, so let's figure out how the energy is distributed at position A. So, I'm going to go ahead and put in my categories of gravitational energy, kinetic energy, elastic potential energy, and dissipated. I'm just kind of setting myself up to think through it. Okay, at position A, the person is very high, so there's a lot of gravitational potential energy. They're not moving, so there's no kinetic energy. The only elastic thing in our system is the bungee cord, and it's very relaxed, right? The bungee is relaxed. And so it's not currently storing any elastic potential energy. Over here at position B, the bungee is stretched. Okay. And then I never showed dissipated at the beginning. So all of the energy at position A is gravitational potential energy. At position B, the person's not on the ground. Right, they're at a much lower height, but there is still some gravitational potential energy. They're not moving. The bungee cord is stretched. Okay, so there must be some elastic potential energy stored in that bungee cord. And so I'm just going to put the rest of my energy as elastic potential energy. This is an isolated system. There were no interactions with other systems, right? So there was no work that transferred energy either into or out of our system. So what I started with, the energy I started with, has to equal the amount of energy that I ended with. And so the conservation equation says that, EG is on both sides of the equation. So I definitely want to distinguish between the initial gravitational energy and the final gravitational energy by using these subscripts 1 and 2. So in the beginning, the initial gravitational energy has been redistributed, and it equals the final gravitational energy plus the change in the elastic potential energy. Okay, there's a part B of this problem which says repeat it, but now the cord is not part of the system. Okay, so I've only got the person and the earth now in my system. Okay, otherwise the situation is completely the same. So again, we're beginning with all of the energy in this person's system stored as gravitational potential energy. And at the end, there is much less gravitational potential energy. The person is much closer to the ground. They're not moving, so there's no EK. Now there's nothing to store elastic potential energy. This system can't store elastic potential energy. The person and the earth, they're not elastic. You can't bend them and have them pop back to the original position. So where did the energy go? It has left the system that we have as work that transferred energy out of the system. The energy is still stored as elastic potential energy in the bungee cord. It's just that the bungee cord is not in the system the way we've defined it. And so my conservation equation says that the initial gravitational energy is equal to the final gravitational energy plus the work that transferred energy out of this system. Okay. So you can have situations where work transfers energy in. We did a couple of those before. And you can have situations where work transfers energy out. Let's look at the last example here, number 7. Here we have a cart that rolls down an inclined ramp and runs into a spring, causing the spring to compress. Okay, and so we're going to say that the system includes the cart, the ramp, and the earth, but not the spring. I want to be really careful. The spring is not part of my system. At position A, it's at rest, and it's at the top of the ramp, so it has some height to it. At position B, I'm just going to say this is on the ground. It's low enough, we're just going to say it's on the ground. And it said, let's see, it says the cart's velocity has slowed to 0. Okay, and so the spring is compressed. And this is probably just for an instant, but the velocity is 0. It's kind of like at a peak of its motion. It's getting ready to turn around and get pushed back up the ramp by the spring. But at this moment, at position B, it's not moving. Okay, so let's decide what kind of energy this system has at position A. It's at rest, so there's no kinetic energy, but it's at the top of a ramp. So there's a lot of gravitational energy at the beginning. And then at position B, it's on the ground. There's no more gravitational energy. It's not moving, at least for an instant, so there's no kinetic energy. I do think that there's some elastic potential energy somewhere, but is it in our system? No, because the cart, the ramp, the earth, those things don't store elastic potential energy. And did it tell us whether there was friction? It says friction does exist. Okay, so I've got some dissipation, because as the cart moved down the ramp, there was friction that had to be overcome. But I started with 5 blocks of energy in the system, and at the position B, there's only 1 block of energy in the system. It clearly has less energy than it started with. What happened to that energy? Energy has left the system. It's been transferred out of the system and into the system that has the spring, right? Because the spring got compressed when the cart applied a force to it. Okay, so I'm going to write the conservation equation. The initial gravitational potential energy equals the change in the dissipated energy plus the work that was done on the spring that transferred energy out of this system.